consist of an NMOS driver. Well, both are NMOS, as you can see from the direction of current, and the drain is at a higher potential than the source in both the transistors. So we have two transistors. This is the gate terminal. So one is ML, okay, that is the load device, and this part of the circuit is your load, okay. It acts as you can say as a resistor or nonlinear resistor. Let's call this RD or RDL, which is the load at the drain of your driving resistor. So driving resistor, you can see the substrate over here is an NMOS device. MD is the other resistor. So then you have this drain, source, and gate over here. So the characteristic of this particular RDL were shown before as follows. And what we said was that you had this, if you take the gradient of this curve, you have delta ID by delta VD, and the inverse of this slope is your nonlinear resistor. Okay, so this is delta VDS. So the inverse is the resistor RDL. Okay. Now the thing is, in MOSFET devices, this is RDL for if you say in the limit that the delta is very small. Okay. Now, in the for example, in the digital logic circuits, and in the digital logic circuits, you don't have ISMDs or thin film resistors, carbon resistors. Okay, the MOS or MOSFET devices, they themselves simulate or emulate resistances or the current sources. Okay, so for current sources, resistances, we don't have this other devices other than MOSFETs. Okay, so it's all MOSFETs. For example, over here, a driving MOSFET MD is having a resistor negative, a nonlinear resistor RDL, which is itself a MOSFET device. Okay, so it's being biased by another MOSFET device. Okay, and this device, as you can see, is the configuration is as such that VG and VD are the same. Okay, and this is clamped to VDD 5 volts, right? But in this configuration, you should notice that your drain to source current in the load transistor and the drain to drain current in the driving resistor, the drain to source current in the driving transistor, they are the same. Okay, they are the same. So IDL is IDD. Okay, these are the series currents. And one more thing is that if you recall in the last time we discussed that, since if you can see over here, well, VGSL for the load transistor was equal to VDSL. Okay, since the source is common, okay, L denotes the load transistor ML. Okay, we're talking of this transistor. So over here you see VGSL and VDSL, they're the same. Okay, so this transistor, the load transistor, is always driven in saturation. Okay, the ideal is the saturation current, which is given by Kn VGS minus VDN whole square. Okay, and that's since VGS is the same as VDS, so you can use this relationship as well. So you can see that as you increase VDS over here, as you increase VDS, your ID is increasing. So that's the nonlinear device resistance characteristic that is being emulated, modeled by the load transistor ML over here. Okay, so this is in fact an enhancement mode NMOS device. Okay, so we call this a load device, nonlinear load device. So with increasing VDS, your ID increases. Okay, but the condition is that your VDS should be greater than the threshold voltage. Okay, VDN, because this VDS is the same as VGS, so you need at least a threshold voltage at the gate at this point to turn on the transistor. Okay, therefore VDS should also be greater than VDN. So over here, if your VDN is 1 volt, then after 1 volt the device turns on and conduction starts. So the current starts over here. Okay, so then it's as you can see, as the gradient is rising, it's about a linear. It becomes it's just like an ohmic region, okay, of a resistance. All right, so ML. So let's not forget that ML, the load transistor, is always driven in saturation region. while MD can be in SAT or non-SAT. Okay, so I mean this can be in SAT or non-SAT. It depends on if you consider the circuit as an inverter. Okay, it depends on the value of the input voltage that defines the biasing of the transistor. I mean the operation regime of this lower transistor or the driver transistor. It could be in the SAT or it could be in the non-SAT. So, for example, if the input voltage of driver transistor is small, okay, if Vi is small, then that means Vi is small, but Vi, however small, should be greater than VTD, which is the threshold voltage of the transistor in order to turn it on. But if it's small, then that means IDD is small, okay, because you're creating a small inversion layer. The field is as such that the channel length, the channel width is small, so you're not creating much of the space charge density in the inversion layer. So the current is small, okay. When the current is small, then that means if you consider this as RDL, then I can write this as VDD minus IDL into RD. This RD models my, actually this, well, this I can write also as BDSL, okay, which is the drop at the load transistor. So, well, this is your V out, isn't that right? This V out over here is my also the voltage at the drain, okay, at the drain of the driver transistor. So when my Vi or the input voltage, when that is small, or when VGST is small, then your current is small. When this is small, that creates a small drop. Okay, so you have the V naught so you see when this IDL is small, the output increases. Output increases. So conversely, if your ID is large, then that produces a large drop at the drain to source terminal of the load transistor, and your output decreases. So your output decreases. So it's the other way around. Okay. I mean, it's like it all depends on the input voltage. If the input voltage is large, it controls the current. Okay. If the input voltage is large, the current is high because you have more space charge density. The inversion layer it consists of more space charge density. So when the current is more, there's more drop over here. There's more drop that occurs, and it produces small output voltage. Okay, so for large Vi, you have small output voltage. For small Vi, you have large Vi. You have large V naught. Okay, so it's like an inverter in a digital logic circuit. Okay. Now, so your device ML is always biased in the SAT region, and transistor MD, called the driver transistor, can be biased in either saturation or non-saturation, and it depends on the input voltage. So that's the idea behind it. Okay, so if your Vi is large, well, your current is large, so your output becomes small. Okay, the output becomes small. So for large Vi, you have small V naught. For small Vi, you have large V naught. Okay, and the reason is you are controlling the current with respect to the gate source voltage VGST, which you can see is equal to Vi. Okay, so the gate voltage for the driver transistor is Vi. Okay, so let's understand this. Um, let's have a look at these ideas in terms of an example. And this example is from the text. It's 3.9. So the objective is to determine the DC transistor currents and voltages in a circuit containing an enhancement load device. Okay, so the configuration is very similar to what we have seen previously. Okay, so you have an enhancement load device which models a nonlinear resistance. Okay, like this. IV characteristics are like this. And then you have a driver transistor which is either biased in SAT region or non-SAT region. So you have this MD, okay, down there, and then you have a nonlinear load or enhancement load device given by ML. Okay, right. So you see in IC this is a digital inverter. This circuit is a digital inverter. So you don't have any carbon film resistor or thin film resistor or surface mounted devices. So all that you have are MOSFET devices. Okay, so this is your inverter in a digital logic circuit. For large Vi, you have small V naught. Okay. For small Vi, you have large V naught. So the transistors in the circuit shown in figure below, the parameters are given: the threshold voltage for the driver transistor and the threshold voltage for the load transistor are the same, 1 volts. Okay. Then you have the conduction parameters given as 50 for the um, for this driver transistor, 50 microamps per volt square, and then you have this conduction parameter for the load transistors, 10 microamp per volt square, right? So let's assume that the channel modulation parameter is 0. Okay, the subscript D applies for the driver transistor and subscript L applies to the load transistor. All right. So this subscript L shows that this is lower and this is the driver transistor. Okay. What you're required is to determine V naught, and then there are two voltages for your input voltages. You have to determine V naught for two input voltages, two separate input voltages, 5 volts and 1.5 volts. Okay. Okay. Now the first thing is you see this parameter. This is the channel width modulation parameter. If you recall, in saturation, the I and V characteristics with respect to the gate to source voltage, you have a quadratic relationship. But in actual MOSFETs, you have this slope as a rising slope. You don't have the flat slopes. But it says in this, to treat these MOSFET devices as ideal, so the lambda is 0. Okay, the lambda is 0. You see in this equation, if the current is 0, the current is made to be 0, then this factor, because threshold voltage is a parameter associated with the transistor, it's non-zero. Kn is another conduction parameter, it's non-zero. VGS is the voltage required at the gate, at least greater than VDN to turn the transistor on. So it's like an overdrive voltage. Okay, overdrive voltage. It's also, you can say that this also determines your saturation point. Well, this has to be greater than VDS sat, so that the transistor is biased in the saturation region. This factor has to be greater than VDS sat. So all of this is non-zero quantities. But in order to make ID equal to 0, VDS should be equal to minus 1 over lambda, and this is given by this parameter, and that creates the slope. So in this example, we're not considering the slope. Okay, so basically we don't have this rising slopes like this or like this. So this is increasing, this is with increasing VGS values. So we don't consider that. What we consider is a flat slope IV characteristic. So in saturation, if this is my, these are my, transitions are for VDS sat for each VG, then after the transistor is biased past this point, VDS sat, your slope becomes 0. The slope is not 1 over R naught. Okay, so your ID is not dependent on VDS. So ID is non-dependent on VDS. So we're only going to consider this part of this expression. Okay, no dependence on VDS shall be considered. So that's the assumption given. So no channel width length is being modulated by VDS. So we don't need to consider this factor. Okay, so let's keep that out. This is not an actual MOSFET device. This is an ideal MOSFET device. Okay, so to start with the analysis, you see we have two input voltages, 5 volts and 1.5 volts, and if you can figure out, this 5 volt is higher input. So what happens is that your ID is higher as compared to when your VA is going to 1.5 volts. Okay, so when for 5 volts you have a more current. Okay, and this current is going to have a more drop across this driver transistor, the load transistor. Okay, let's understand this as a load RDL, and as a result, your V naught is going to be small. The output voltage is going to be small, and this output voltage is also equal to the drain VDSD, which is your drain to source voltage for the driver transistor. Now, if your VDS is small, then you are somewhere here near DC. Okay, so of course this is a small region for VDS. So that means your intuitively your your driver transistor is biased in non-sat region. Okay, this is non-sat region. So the current and voltage relationships are going to be defined for non-sat region for the driver transistor MD. Okay, and also note that this current and this current are the same. These are the series currents. Okay, so we must recall that IDD, that is the drain to source current in the driver MOSFET. This is equal to the drain to source current in the load MOSFET. Okay, this is the load MOSFET. So enhancement load device. So this is IDL. All right. So this current IDL is for SAT, and this the other left hand side current voltage relationships are to be used for non-SAT. Okay, this is for non-SAT. So let's recall those relationships for SAT and non-SAT currents. So you see, to start with, okay, over here you have this IDD equal to IDL. You see the drain current in the load device is equal to the drain current in the driver transistor. So with these currents in the generic form, we have this expression. So this is for your MD, the driver transistor. This expression is for the driver transistor. All the subscripts are ending with the D over here. So this is non-SAT current. This is non-SAT IV characteristics. And you see in non-SAT, unlike SAT, we have a dependence on VDS, right? Because in saturation, you don't have any dependence on VDS. After saturation, your current stays constant, irrespective of what VDS is. So, that's not the case in the non-sat region. In the non-sat region, you will see this VDS voltage is coming into the expression. But then, if you compare this with the saturation part of the current, which happens to be in IDL, which is the load transistor, this is your saturation IV characteristics. Okay, and these are in quadratic with respect to the gate source voltage VGSL. All right. So this doesn't depend on VDS. This is non-dependent on VDS, so you don't see any expression of VDSL over here. Now you equate them, and you also note that VGSD is VI, right? I mean this VGSD, since VS is 0, VS is 0 over here. It's common. VS is 0, so VGS is basically VG. So VGS is VG, VG is your VI, that's the input voltage. So VGSD is your input voltage, then VDSD is output voltage, okay, because the source is 0, so this is equal to VD, this is equal to VD. This is the potential at the drain of the driver transistor, okay, and source is at 0, so this is again VDS, right? So VGSL is VDSL, okay, over here, because the source is common, source is at common potential, and VGS, VG and VD, they are short circuited over here. They are the same potential. VG and VD are at the same potential. So VGSL and VDSL are the same, and that is given by VDD minus V naught, okay, because this VDD supply is fixed. So VDD minus V naught, the potential difference of this point and this point gives you VDSL, okay. So that is your VDSL, or VGSL is the same thing. Now, if you substitute these expressions over here and this over here, well, you see this VGSD is your input, so it becomes 2VI minus VTND is the threshold voltage for the driver transistor. Similarly, TNL is the threshold voltage for the load transistor. Then VDSD is your output voltage, so that can be V naught. Then you have the conduction parameter for the load transistor. Okay, this expression is substituting for VGSL over here, right? Because this is equal to, this is following from this expression. VGSL or VDSL, the same thing, is VDD minus V naught. Okay, so all we left is a quadratic in the output voltage, because threshold voltages are given for the transistor. Threshold voltage, we have the threshold voltages, these are 1 volts for both the transistors. We have the conduction parameters, we have the threshold voltages, and then we have the input voltages as well. So everything is there apart from V naught. So you substitute test for the threshold parameters K and D. The input voltage is 5 volts, threshold is given as 1 volts, and the only thing that is unknown is V naught in this expression. Okay, you have Kn as 10 micro volts per amp squares. Yeah, 10 microamps per volt squares. And then you have this VDD, which is fixed as 5 volts. Okay, VTNL, the threshold voltage is 1 volt. So you are left with a quadratic in V naught. The only unknown over here is the V naught, and V naught is VDS. Okay, VDSD, this thing. So let's find that out. Let's solve this quadratic. If you write this in a quadratic and solve this, you have two solutions. One is V naught is 7.65 volts, the other is 0.349 volts. Well, you cannot use this 7.65. Well, to see this in a very straightforward fashion is that the output cannot exceed your battery supply, that is 5 volts. I mean, the transistor cannot generate energy in the circuit, and you cannot go past beyond VDD. Well, that's not the case. Well, that's not going to happen. And the other intuition is, so you see, it says the output voltage cannot be greater than the supply voltage. So this is not a valid solution. Okay. The other reason for selecting V naught as 0.349 would be to see the transition point for the driver transistor. You see VDSD over here is your V naught. Okay. This VDSD is V naught. Okay, because this drain, this potential is V naught. Okay, source is at 0. VDSD is V naught. Is equal to 0.349 is less than VGSD minus VDND, which is your saturation point for the driver transistor. So if I may write this as VDSD sat, that defines my saturation or transition point from non-sat to sat. So if the biasing is as such that the output voltage or the drain voltage is not is less than the saturation voltage or the transition point, it's given by the VGSD minus VTND, that's 4 volts. Well, then your transistor is indeed biased in the non-sat region, and it confirms that. Okay, for 7.65, if it was to be 7.65, which cannot be the case, then you cannot use this relationship. Then you won't have this non-sat IV characteristic. You would be using an expression similar to this saturated current. Okay, for saturated current, which is independent of VDS. But we use this for small output because the input is large, the output was small. So we used the non-sat expression in which the current was depending on VDSD, and VDSD is equal to V naught. And you can find this the output of the transistor, which is less than your the saturation or the transition point. The transition occurs somewhere over here. Okay, so I'm talking about this point. This is saturation point. For each VGS, this is the saturation point, and it's given by the difference VGS minus VTN. Okay, so this is VGS minus VTN. So that's 4 volts. So this 0.349 is less than 4 volts. So you can use the non-sat IV expression. Because for small VDS you cannot go beyond VDS sat. So this is indeed valid. Okay. So this expression, this solution is valid for because your driver transistor is a non-sat. This is a valid solution for non-sat operation regime of driver transistor. Okay, we cannot have this because well, we cannot create energy. But that's one. You cannot go beyond the supply voltage. The other is, if you use this, then your expression would have been wrong, the IV current characteristics. Okay, the current can be determined if you are looking for the drain current. You can find any. I mean, you can either use this. Is both the currents are equal. You either use the non-sat expression or use the sat expression for the load transistor. So in this case, if you use the this load or enhancement load MOSFET device, then this is equal to the conduction parameter, the saturation, same saturation expression for IV characteristic, VGSL minus VTNL, and VTNL is again 1 volts over here, and you have the output voltage as 0.349, and VDD is 5 volts. Okay, and for KNL is 10. You see, this expression is substituting your VGSL, right? This is your VGSL, and this is very evident if you look at this circuit. I mean, this VGSL, since this is also equal to VDSL, and VDSL, as I explained before, is nothing but VDD minus or if I may write this as, okay, VDSL. Yeah, I'm writing the KVL at the output loop. Okay, so I'm here. I'm writing this as such. So VDD minus VDSL leaves me with what? V naught. Okay, so or you can say that VDD minus V naught, VDD minus V naught is your VDSL. So I'm substituting this for VDSL, or which is the same as VGSL over here. So this goes over here. This expression goes over here, VDD minus V naught, and then you find the drain to source current as 133 microamps. Okay, so that was the solution. We were required to find the output voltage for Vi equal to 5 volts, and then for 1.1.5 volts, and this and corresponding to the output of 0.349 volts, we have the current of 133 microamps. Okay, which is the same as the drain current in both the MOSFET devices. Then let's consider this, or let's talk about a lower voltage, 1.5 volt. Now, since the threshold voltage of the driver transistor is 1 volt, and the input voltage is very close to the threshold voltage, that means the transistor current is going to be relatively small, so the output voltage should be relatively large. Okay, it's an inverter device. So for this reason, we'll assume that the driver transistor MD is biased in the saturation region. Okay, so this expression is now for the SAT region, not for non-SAT. So this is SAT and this is SAT. This is the driver device D. Okay, you see all the subscripts are ending with D, all the subscripts are ending with L. So this is your load device, and you're using this for the SAT region as well. So again, once again, VGSD is Vi. Okay, so this is equal to Vi. Your gate is at the input voltage, and VGSL is VDSL. Okay, so VDSL, you see again you find this one potential difference of VDD and V naught, and then you substitute these things over here in the current expressions. Okay, so the current expression becomes like this. Then this VGSD is your Vi, and then substitute it for the values. 1.5 volt. Take the square root of both sides, so you don't have these squares anymore down here in the expressions. But the conduction parameters, they're coming the square roots. Okay, so VDD is 5 volts, 5 minus V naught. So you have an expression in V naught. So this gives you V naught as 2.88 volts. Now, if you want to check this, if this the transistor is indeed in saturation, let's find the transition point. So the transition point VDSD, which is V naught, I mean this VDSD over here, VDSD is your V naught. See the drain, this is your VD. This is the drain potential is the same as V naught. Okay, source is at 0. So this V naught is your VDSD. Okay, so is this greater than VDSD SAT? That's the question. And if that is the case, well, then indeed the current expression that we have used for this inverter topology of MOSFETs is true. Okay, so what we are saying is that both the transistors are operating in saturation region. So the output is 2.8 volts, which is greater than VGSD minus VDND, and VGSD is 1.5 volt. In this case, we have a small input voltage. Difference is 0.5 volts. So 2.88 is greater than 0.5 volt. That means your driver transistor is indeed based in the saturation region. So the initial assumption was correct. Okay. Now, if you compute the current and use the saturation expression for either the load device or for the driver device, this is the driver. This is for MD MOSFET. Current in the MD or the driver MOSFET, same as the current in the load MOSFET. That can be obtained from the input, that is 1.5, the minus threshold, into 50 whole square of that gives you 12.5 microamps. Okay, so this is your saturation current, and previously we had this. Well, the currents are the same, but I mean, based on the input and basically based on the input voltage, Vi, as I've explained previously. If Vi is small, that means the driver transistor is in saturation region, and if it is in saturation region, well, your V naught is going to be greater than the transition point, which is 2.88 volts over here. Okay, and for 5 volts, for 5 volt case, we found this out to be 0.349. Okay, because this was not set. So this case was for I mean this case was for small VDS or large input voltage. Okay, so this is indeed an inverter topology. This is what happens in an inverter digital logic circuit. For large VI, we have small V naught. For small VI, like in 1.5 volts, the V naught was 2.88. When VI is 5 volts, well, then this switched out to be 0.349 volts. Okay, so it's indeed an inverter circuit. Okay. Now, you see this. Okay, in figure 36, what we started earlier, I mean, the discussion on this circuit with enhancement load device, we used the P-spice in your textbook. It said they've used this P-spice analysis to come up with the transfer characteristics of the circuit, and the transfer characteristics are between the output voltage, which is again VDSD, versus your input voltage, which is VGSD. Okay, and you can see that you can see the inversion characteristic in the transfer function. The transfer function are plotted with respect to the input voltage and the output voltage of the transistor, driver transistor, and you can see if your input voltage is large, if the input voltage is large, which is given in this direction, goes up to 5 volts. Well, your the output is small. For 5 volts, we found out this to be equal to 0.349 volts. Okay, and for small input, let's say we would here somewhere for 1.5 volts, probably somewhere here, 1.5 volts, and this was equal to around, this was about 2.88 volts or 2.9 volts. Okay, so for small input voltages, for small VI input voltages, we have large output, and for large input voltages, large input voltages, we have small output voltages. We have small output voltages over here like this. Okay, so this is small VI, large V naught, and for large VI, small V naught. Okay, so this is an inverter topology. So what it says is that the voltage transfer characteristics for NMOS inverter and with enhancement load shown in figure 36, they were obtained by the piecewise analysis. Okay, now we are looking at the voltage transfer characteristics. The results are shown in figure 37. This is figure 37. This is over here is figure 37, and these are the voltage transfer characteristics of your NMOS inverter with enhancement load device. So as the input voltage decreases from its high state, the output voltage increases, charging and discharging capacitances in the transistors. So what it says is the current in the circuit goes to zero when the driver transistor is off. And when does that happens is that this occurs when the gate voltage is less than the threshold voltage, and that in the example was given as 1 volts. Okay, so VI which is equal to VGSD, you see over here, if that becomes less than the threshold voltage, or it is around 1 volt, your transistor is off. So at this point, the output voltage is 4 volts. So you see over here at very small near 0 DC, that's 0. You have the output voltage clamped at 4 volts. Okay, you're not getting the complete VDD because since there is no current, the capacitances they cease charging and discharging. The MOS capacitances they cease charging and discharging. So the output cannot get to the full VDD value of 5 volts. The maximum output value you can get is VDD minus VDN, which is the threshold voltage. That's 4 volts. Okay. So you can see this for transfer characteristics that when the transistor is off, and this occurs somewhere in this region. I mean, in this region where the transistor was, well, in this region the transistor, your driver transistor is already in non-sat. Sorry, in the driver transistor is already in the sat region. Okay, and you're already getting very high output voltages, but as a limit, this never reaches to VDD. Okay, because the capacitances they cease charging and discharging. So what you get is at max the difference of VDD minus the threshold, about 4 volts. Okay, so that's the point where the transistor is going to be cut off. I mean, this might be the threshold voltage. So less than that, you're getting the constant output, that is 4 volts. Okay, So when the input voltage is just greater than 1 volt, both the transistors are biased in saturation regions as done in the previous analysis for Vi equal to 1.5 volt. We have showed that for Vi equal to 1.5 volt, both the transistor MD, the driver, and the load transistor ML were in saturation regions. So the output voltage is a linear function of the input voltage. Okay. So for an input voltage greater than approximately 2.25 volts, the driver transistor is biased in non-sat region. Well, you can see this over here. I mean, beyond a certain 2.25 volt value, your output voltage is decreasing with increasing input voltage. So that occurs when the driver transistor goes in the non-sat region. Okay, non-sat region means lower VDS values. Okay, lower VDS and lower ID values. So the output voltage is a non-linear function of the output voltage is a non-linear function of the input voltage. So in the circuit shown in 36, we can determine the transition point for the driver transistor that separates the saturation and non-saturation regions. Now the transition point generically is given by the equation. That's the difference between the gate source, it's the overdrive voltage, okay? Difference between the voltage applied at the gate and the threshold voltage. That's the threshold voltage. So that's your saturation or the point beyond which the transistor goes into saturation. So that's the point that differentiates between saturation and non-saturation. So again, the drain currents, the two transistors are equal using the saturation drain current relationship for the driver transistors. When both the transistors are in a sat region, what we are interested is to find the transition point where this transition actually occurs, where the transition for the driver transistor goes from saturation, go from non-saturation to saturation. So substituting this VGS in this expression, VGSL over here in this expression for VDD minus V naught over here, and then taking the square roots of both sides, we can define the input voltage Vi as VIT and the output voltage as V naught T as VDS sat, which is VIT minus VTND, and then substituting this in the above equation, we can find the transition point of the driver transistor. Okay. So, well, you can also substitute the values of for the given example what we have discussed before over here, and you can find it for yourself that this is indeed the case, and this is indeed the transition point. This expression this does shows the transition point for the driver transistor where the transition occurs from non-sat to sat region. Okay.